Welcome everyone. In this video we're going to be talking about enthalpy. Okay, we're going to talk about where enthalpy comes from, its definition, how we can compute enthalpy for certain processes and such. Okay, definitely talk more about enthalpy in future videos, but here we're going to introduce what is enthalpy. Okay. So we talked before about constant volume processes, right, where there's no extra work, right, the work done is then zero, and delta U is just related with Q sub V, right? The heat transfer under constant volume conditions. Okay. Under constant pressure conditions, what we'll show in a minute is that the heat transferred under constant pressure conditions is equal to what is called the enthalpy, right, of the system, right, and that change in enthalpy of the system. Okay. Right, so enthalpy itself is defined as follows. It is defined as the internal energy plus pressure times volume. Okay, this is the definition of enthalpy, right? This is what it's defined as. Okay, it's related with internal energy, but it's not the same thing as internal energy. It includes this PV term. Okay, now it does share some properties similar with internal energy, right? It is a state function. Okay, enthalpy is in fact a state function. It is also extensive, right? Just like internal energy is. Okay. But a difference with internal energy, right? I can have an absolute zero internal energy, right? I can have something that has zero energy, okay? Whether or not I can reach absolute zero internal energy is another question, right? But it is well defined, okay? Enthalpy, on the other hand, does not have some sort of absolute value, okay? Enthalpy does not have like some minimum zero value or things like that, okay? This will come up later when we talk about enthalpies of reactions and other things like that, and how we define zeros for enthalpies and such. Okay, but it's an undetermined value, right? There is no absolute zero, right? It's like Celsius, right? I mean, there's a 0 Celsius, right? But it's not like an absolute zero, right? Kelvin has this absolute zero. There's no minimum value lower than this value, right, of Kelvin, right? 0 Kelvin, that's the lowest temperature that exists. Okay. So we take our definition of enthalpy, we're going to take the total differential of that equation, right? Noticing the fact that I have dPV, so I got to take, factor those things out and put PdV plus VdP. Okay, so this is, right, this is just the total differential of dH. Okay, it's just du plus PdV plus VdP. Now, right, we're going to assume, right, we're under constant pressure conditions, right? So that is why dP is equal to 0. So that dP term goes away, and we're just with the dH equals du plus PdV. Now, right, if I were to integrate these things under constant pressure, okay, I would have delta H is equal to delta U plus P delta V, okay? Right, we use the fact that delta U is just equal to Q plus W, okay? The fact that delta U is equal to Q plus W, and using the fact that work is just minus P delta V, okay? Now, work is minus P external delta V, right? But here we're using P. Well, how can we do this, right? Well, we're going to assume that we're in mechanical equilibrium with the surroundings, okay? If we're in mechanical equilibrium, right, that means P is equal to P external. So that is just minus P delta V now, and now this minus P delta V cancels this positive P delta V, and I just get delta H is equal to Q sub P, right? Delta H is the heat transfer under constant pressure conditions, assuming the pressure of your system and your surroundings are equal, right? That you're in mechanical equilibrium, right? So think of this as like heating a balloon, okay? When you heat a balloon, its volume expands, right, but its pressure remains constant, and it's the same as the external pressure, right, typically 1 atmosphere, okay? So heating and cooling a balloon is an example of when I would have a constant pressure expansion or compression, right, where I'm always in mechanical equilibrium with the surroundings, okay? And in those cases, delta H is equal to Q sub P. Right, so this, again, the slide here just summarizes, right, that I'm assuming constant pressure, assuming a mechanical equilibrium, and that there's no extra work that's being done to get to this final relationship Okay, as how I derived this relationship. Okay. Okay. So, right, right. In the last set of videos, right, we talked about how CV is related with del U, del T under constant volume, right? Well, CP is the same type of thing, just with enthalpy, right? That the heat capacity, right, is related with how enthalpy changes with temperature. Okay, if enthalpy did not change with temperature, then that heat capacity would be 0, right? Or potentially could be a constant if it linearly changed with temperature. Okay, but CP, right, is the relationship between enthalpy change and a temperature change under constant pressure. Okay, right. Rewriting this, we get dH equals Cp dt, right? And if Cp is constant, right, then we get that delta H is equal to Cp delta T. Okay, so this is true when Cp is constant. Okay, and again, you're assuming here that we have no chemical reactions, no phase changes, and things like that going on, right? Okay. Now, this relationship for delta H and delta T, okay, or delta H equals Cp delta T, is going to work even if I do some process not under constant pressure conditions, okay? Because just like internal energy, enthalpy is a state function, which means that if I do a change of state from state A to state B, right? Let's say I did it under constant pressure conditions, right? I would get delta H equals Cp delta T, right? Well, if I did it under constant volume conditions, I would get the same thing, that delta H equals Cp delta T, okay? Right? It does not matter how you do that change, just what is the initial and final state. And in that case, delta H is always equal to Cp delta T, right? Under the assumption Cp is a constant, okay? Right? That's the only way this equation changes, is if Cp itself is not a constant. Okay. Sorry. Right. Now, Cp isn't always going to be temperature independent, right? And in fact, typically has a temperature dependence that's kind of approximated by this formula here, right? Some constant value plus some linear increase with temperature plus some dependence on 1 over the temperature squared that has to deal more with low temperature conditions, okay? Right, and the constants for different substances are given in this table here, right, for A, B, and C, okay? And this would give us a temperature dependent Cp, right? And so delta H in this case would be the integral of that Cp dt, right? And we'd have to plug in what Cp was, right? And take that integral of A plus Bt plus C divided by T squared. Okay. Right? And as I mentioned when I talked about the heat capacity at constant volume, right? One major place where this deviates, this constant value, is near 0 Kelvin, okay? At near 0 Kelvin, that heat capacity is proportional to the temperature cubed, okay? And this can be derived from quantum mechanics and statistical mechanics. Einstein derived this a long time ago for solids, right, near very low temperatures, using quantum mechanics and definitions of some springs and things like that. You're able to get this formulation of the relationship between the heat capacity and the temperature being T cubed, okay? And then another note about Cp, okay, is that it is related with Cv for ideal gases specifically. Cp plus Cv equals Nr, or the molar volume, right? Cpm equals Cvm plus R, okay, right? Often heat capacities are given joules per Kelvin mole, right? So R here, you want to be using the 8.314 joules per Kelvin mole value, okay, right? Because otherwise your units aren't going to work if you try using the liters atmosphere version of R, okay? Right, so some other final comments about the heat capacity at constant pressure, right, is that it can be temperature dependent, but often we treat it as independent, okay, as a constant, right, but technically it can be, right, and I presented that formula earlier showing how it typically changes with temperature, okay. right? During phase changes, heat capacities go to infinity. This is one way one measures a phase change, right? One tries to, if you're trying to measure whether or not you're undergoing a phase change, if you measure the derivative, right, the change in internal energy with respect to change in temperature, change in enthalpy with respect to change in temperature, you'll find that those values go to infinity during a phase change, okay? So it's a very easy way to spot a phase change, okay? Right, and then this last comment here, right, just talking about plot CP versus T, right, you would get the total enthalpy change, right, if I have some plot of CP versus T, right, just temperature CP or something like that, right, right, if I wanted to know how much enthalpy change was from this temperature to that temperature, right, all I do is just add up, right, the area underneath that curve, right, integrate under that curve, okay, and that would give me the total area, and the integral of that, you know, curve, right, the area underneath that curve is what it will be equal to delta H, okay. All right, so this does it for the first video, talking about enthalpy and heat capacity, okay.